Hello, this is Professor Behrang. I'm here again with another video in the area of thermal and fluids. This video is going to be about the Bernoulli equation, the concept of it, physical concept of it. And it's going to be a short video. Make sure you comment, like, subscribe, and these things that will help the channel because of the algorithm. And also, if you have any topic in mind in fluid mechanics that you want to know more about, fluid mechanics, heat transfer, thermodynamics, all of them, and make just a comment, make a comment so I can possibly make a video about it for you. So let's get started. With Bernoulli equation, the concept of Bernoulli equation is about physical energy. So you are familiar with that from, I don't know, physics, right? Or dynamics. Somewhere you have learned about this before. That we have two types of energy that we normally deal with in thermal and fluids. And there is, mechanical energy and there is heat energy. So there is a difference between, these two. The unit that we use for both of them, is either joules or watts. We know that. But, and they are somehow interchangeable. You can convert mechanical energy to heat energy, or you can convert heat energy to mechanical energy. But there is a major difference between these two, although they use the same units, SI units. What we know about mechanical energy is if there is no friction, mechanical energies are interchangeable. For example, if I have, this pen here and, the potential energy of this pen here is more than its potential energy when it's here, right? And then when I release it, eventually that potential energy turns into velocity here, and I can even calculate writing, mg z that I have here, and I set it equal to 1 over 2 m would be the mass of this, v squared, when it hits my palm. The reason I'm not writing these formulas is that I assume that you're familiar with these things. So I can calculate how fast it's going to hit my palm. You learned that in physics already. And we can say mechanical energy, if there's no friction, theoretically, they are interchangeable. You can convert all the potential energy to kinetic energy, and you can convert all the kinetic energy to potential energy. For example, if I throw this up like this, I don't want to hit myself, but I give it some velocity and I throw it up, and then it goes to a certain height. I can potentially, theoretically, calculate the height is going to go up by using the basic laws of mechanical energy. So mechanical energy's different forms of it are interchangeable. The forms that we are really familiar with are kinetic energy and potential energy. And okay, what about heat energy? Heat energy, what we know about it is that you can convert all the mechanical energy to heat energy, all of it. Let's say I have 20 joules of mechanical energy, and I can convert all of it to heat energy. It is possible via friction, via some method. But it is impossible to convert all the heat energy that I have to mechanical energy. And that's basically the second law of thermodynamics, right? So there's that difference that we need to know when we approach Bernoulli equation. Bernoulli equation is not about the conservation of heat energy. It's about the conservation of mechanical energy. Eventually, when you write the first law of thermodynamics that has heat energy in it, you can derive Bernoulli equation out of the first law of thermodynamics. But the case that we're studying here is the case of a fluid streamline that from point 1 to point 2, that there's no friction from point 1 to point 2. There's no heat addition or heat extraction, or there's no pump. There is no turbine that extracts energy from the system or adds energy to the system. That's what it is. So this was just an introduction where we're going. So now let's take a look at a streamline. I'm going to talk about it a little bit, what a streamline is, and how we can look at Bernoulli equation. A streamline basically in a fluid is Bernoulli equation works for a single streamline. So Bernoulli equation. You're on this is a fluid streamline that goes from point 1 to point 2. What's the definition of streamline? You know, streamline is a curve that is tangent to all the velocity vectors in the flow. So that's a streamline. That's a different topic. So let's say you know already what a streamline is. Let's apply conservation of energy to this. How many different types of energy fluids have? We said at point 1, we do have the kinetic energy. And I'm going to write the energy per unit mass because it's a fluid. So in the unit of joules per kilogram. So I have kinetic energy. Kinetic energy at point 1 would be the velocity of fluid at point 1 over 2. That's kinetic energy. I got that. What other type of energy do I have here? I have, you know, potential energy. Potential energy per unit mass would be G times Z1. So that is potential energy, right? Like this. Now, if you have looked at the last video I posted, and I'm going to put the link to that video to this in the description here, we talked about something that is called flow work. And that exists in fluid mechanics and thermodynamics. And where it comes from, go ahead, go back, look at that link and watch that video so you get the concept of flow work. So I'm assuming that you already know the concept of flow work. If you don't, watch that video, you'll get it. So there are 3 types of mechanical energy that we are dealing with. And the third one is P times V, also P over density, P being the pressure and rho being the density of the fluid in the case of incompressible fluid. Not incompressible fluid. There's no such thing as incompressible fluid. Incompressible flow. That's a different concept. So this is called flow work. Now, what Bernoulli equation looks at is on a single streamline in a steady state flow. So there are some, you know, conditions that you need to know. The flow has to be steady state, okay? That's the first condition. Second condition, for this version of Bernoulli equation that I'm writing for you, the flow has to be incompressible. Incompressible, okay, that's the next one. What does incompressible mean? It means that density has to be a constant value, okay, sure. We'll keep density constant. That's 1, that's 2. Then no heat addition. You don't add any heat or extraction, no cooling, no heating, basically. That's the same idea. No pump or turbine, nothing that adds energy or extracts energy from the system. And what's the last one? The last one is no friction. So these are the conditions for the incompressible form of Bernoulli equation. We need to have these conditions. So I'm going to move these conditions here because I don't want my face to block them. And if these conditions are there, you can use Bernoulli equation. Bernoulli equation says, okay, then mechanical energy is going to stay consistent, which means all the mechanical energy that I have at point 2 will be, if you add them up, will be the same amount of mechanical energy that I have at point 2. At point 2, I'm not going to have V1. Maybe the velocity has changed. Maybe the pressure has changed. Maybe the height has changed. But what matters in this case is from point 1 to point 2 on that single streamline, the flow work plus kinetic energy like this plus the potential energy equals flow work at point 2 plus kinetic energy at point 2 plus the potential energy at point 2, like this. So that's the concept of Bernoulli equation. How can you apply it? First of all, Bernoulli equation, we said steady state. It has to be incompressible flow. We have a version of Bernoulli equation for compressible flow. That's a different one. No heat addition or no heat extraction. In other words, no cooling or heating either, right? So no cooling or heating. No pumps, no turbines between 1 and 2, and no friction. These are the conditions that you need to keep in mind. Also, for Bernoulli equation, just if you look at Bernoulli equation, there is another condition that you need to keep in mind, and that's this. It has to be written on a single streamline. When you talk about pipes, like the average velocity going into the pipe and coming from the other side, you have millions of streamlines. That's a different version of Bernoulli equation, which we call the modified Bernoulli equation. That would be a different video because the kinetic energy correction factor shows up in there, and I have to talk about that, what it means, But the concept of Bernoulli equation is this, that is the conservation of mechanical energy when you're not messing with the flow with cooling, heating, friction, heat addition, heat extraction, pumps, turbines, and also, I'm going to add another condition here. When you say no friction, it means, the inviscid flow. You are ignoring viscous effects. So no friction is basically just ignoring viscous effects. So it's condition number 5. So it's not a new condition, but it's a different way of, expressing inviscid flow also, or no viscous effects. You can talk about it that way. So this is it. That's the concept of Bernoulli equation on a single streamline. Can we apply it in pipes? Yes, but we have to modify it into modified Bernoulli equation, where you can actually apply it to millions of streamlines. You can have the average velocity with the kinetic energy correction factor, and then you can apply, head loss, which is the friction that is caused by viscosity. So you can add that later. But it starts from this. Bernoulli equation, there is a mathematic way actually to derive this. I mean, what I just talked about, I didn't prove anything, right? I just said, from physics, you learn the conservation of mechanical energy, and this is it. And I also introduced the flow work in the previous video. Okay, sure, let's do this. But you can actually sit down and apply Newton's second law on a fluid particle on a single streamline, and you can derive it mathematically, this equation that I wrote here for you, you can derive it mathematically. And so for now, again, this is it. As I said before, make sure to, hit the like button and subscribe and comment. And one more time, if you have any topics in mind, in fluid mechanics, heat transfer, thermodynamics, just make a comment. I'm going to make a video about it for you. Thank you very much. Have a good day.